Hi everyone and welcome to today's video. My name is Emmanuel Olega and I'm a math teacher and a software engineer. I've been creating a series of mathematical videos to actually help an A-level student of Senior 5 and Senior 6 get better at their A-level mathematics. Now today's video is a video that I believe is a follow-up to someone who has already had a knowledge of differentiation and integration. So you need that foundation before you get into what I'm going to introduce today. So in today's video, I'll be introducing the topic of differential equations. There will be a lot of examples that I'll show you, and many of these will be UNEB questions that I believe will actually help you in your preparation for UNEB exams. So without wasting time, let me introduce to you the topic of differential equations. Alright, so today we move into the topic of differential equations, and as I've said, this is a topic I expect someone to have done after having a foundation of integration and differentiation, because that will be very helpful in this section. So this is where we are right now, and then I believe after that we shall actually deal with the applications of differential equations all in the same series. Alright, so let's introduce it. Alright, so differential equations. A differential equation is an equation with a function and one or more of its derivatives. So what happens is differential equations are usually stated this way. So they can be in the form y plus dy over dx being equal to 5x. So basically they are actually in this format, where this is the equation and then this value dy dx is the differential derivative. So this is an equation with the function y and its derivative dy dx. Alright, so now that we've looked at how they can actually be stated, let's look at order and degree of a differential equation. The order of a differential equation is determined by the highest derivative present in a differential equation, while the degree of a differential equation is determined by the power of the highest derivative present in a differential equation. Alright, so let's see what I mean in more detail. Now as you can see, for example, here you can actually see that this is an example of a differential equation that actually has a first derivative here and a second derivative right here. So what happens is when it comes to order, we actually look for the highest derivative that is in the differential equation. So in this case, that is the second derivative. So that would mean that this example is in order 2. So next, when we look at the degree also represents now the exponential of that highest derivative. So if the highest derivative is 2, that means, and we can already say that its power or its exponential is 3, that would mean it is of degree 3. Alright, so let's look at this in more detail. So let's look at order. So the order is the highest derivative. So is it a first derivative, a second derivative, or whatever it could be? Let's look at some examples. So we're being told, given dy dx plus y squared is equal to 5x. So this is the differential equation. Then we're being told to state the order of the differential equation. Alright, so let's solve this. Now you can already see that here the highest derivative is definitely the first derivative. So it only has the first derivative dy dx. So therefore it is first order. Alright, so let's look at another one. This is question 2. We're being told, given d squared y over dx squared plus xy is equal to sine x, state the order of the differential equation. So you can already see that this has a second derivative. So it is second order. Let's look at another one. So we're being told d cubed y over dx cubed plus x dy dx plus y is equal to e power x. State the order of the differential equation. So you can already see that this actually has a third derivative. So since it has a third derivative, d cubed y over dx cubed, so therefore it is of third order because that is its highest derivative. Alright, let's look at degree. So the degree is the exponent of the highest derivative. So take note of that. It is the exponent of the highest derivative. So what that means is you should first know the order before you actually know the degree, and then you just look for the degree of that highest derivative. Let's look at some questions. So we're being told, given bracket dy dx squared plus y is equal to 5x squared, state the order and degree of the differential
equation. So here we can already basically see this is actually a basic one. So the highest derivative is definitely dy dx, and it has an exponent of 2. So it is first order second degree differential equation. Let's look at another one. Given d cubed y over dx cubed plus bracket dy dx, then we're squaring that, plus y is equal to 5x squared. State the order and degree of the differential equation. As I've said before, the first thing you need to know is the order. So you can already say that this is actually the highest derivative is the third derivative right here. And then remember that the degree has to be the exponent of the highest derivative. So that means we will not look at this here. So we shall look at the degree of this one right here. And then we can actually say that it is basically to the power 1. So that means that this one is the highest derivative is d cubed y over dx cubed, and it has an exponent of 1. So it is third order first degree differential equation. So now that you have that, basically I encourage you to try out these examples right here. So try these out, practice them to get better. So state the order and degree of the following differential equation. So I've given you basically 3 numbers to try out and perfect your knowledge. Alright, so today we look at the formation of a differential equation. So consider the equation, then this is like the function f x y, then there is c1 there which represents the arbitrary constant being equal to 0. Let that be equation 1, where c is an arbitrary constant. We form the differential equation from this equation. So this is it. So for this, differentiate equation 1 with respect to the independent variables that occur in the equation. So basically when you have one arbitrary constant, we actually differentiate it, and then we eliminate that arbitrary constant c1 from equation 1 and its derivative. Then we shall get the required differential equation. Now take note that this happens when there is actually only one arbitrary constant. So what is an arbitrary constant? An arbitrary constant is a value which remains unaffected by the changes in values of the variables of the equation. So the goal is usually to eliminate it, as we shall see in different questions. Alright, so suppose we have another function which is f(xy), and then it has two arbitrary constants c1 and c2 being equal to 0. This is equation 2, where c1 and c2 are the arbitrary constants. So we first find the first two successive derivatives, then we get the required differential equation. So what basically this means is we differentiate twice. And then I believe that after differentiating twice, we would have eliminated both of the two different constants and gotten the differential equations. So take note of this. The order of the differential equation to be formed is equal to the number of arbitrary constants present in the equation of the family of curves. But as I've said, this will make far much more sense as we look at different examples. So question 1. So being told to find the differential equation of the family of straight lines y is equal to mx plus c. So part 1, we're being told when m is the arbitrary constant, part 2 when c is the arbitrary constant, and part c when both m and c are arbitrary constants. So in part 1, that basically means that we have to find a way of eliminating m from that equation. So as we've said before, we're going to first differentiate that twice. So this is our equation, y is equal to mx plus c. So we're going to differentiate it and get dy dx. So differentiating equation 1 with respect to x, we can say that dy dx shall actually be equal to m in this case. So you can actually see that when you differentiate it once, this c actually fades away and remain with m right there. And then since we said m is the arbitrary constant, it actually means that we actually have to eliminate it. Alright, so therefore eliminating m from equation 1, we can actually see that we'll replace it with dy dx. So we'll have y is equal to x dy dx plus c. This can also be rearranged this way. So we'll have it as x dy dx plus c minus y is equal to 0. So therefore the required differential equation is x dy dx plus c minus y is equal to 0. So in part 2, we're being told, how about when c is the arbitrary constant? So that means the target is to eliminate c. Now if we differentiate equation 1 with respect to x, we can already see that we have dy dx being equal to m. Now we can already see that when we differentiate the first time, the value of the c arbitrary constant actually already disappear. So that means we've actually already achieved what we actually want. So since c is eliminated from the given equation, therefore the required differential equation is dy dx is equal to m. So therefore the required differential equation is dy dx is equal to m. Now in part 3, how about when both m and c are arbitrary constants? What happens? As we said before, when it comes to two arbitrary constants, we're actually going to be differentiating twice. Remember, the goal always is to eliminate all the arbitrary constants. So when you differentiate once, we'll have dy dx is equal to m. So that's what happens when you differentiate the first equation once. Now what happens is when you differentiate the first time, you can actually see that m still remains. So you actually have to differentiate for the second time. So the second derivative will give us 0, because that m will now disappear, because the m is a constant. So now the second derivative shall be equal to 0. So therefore, since both m and c are eliminated from the given equation, therefore the required differential equation is the second derivative d squared y over dx squared is equal to 0. So therefore the required differential equation is that, as we have right there. And basically this is actually how we deal with arbitrary constants in the most basic way. Now we'll understand further when we do other examples. Let's look at other examples. Alright, in question 2, we're being told to form a differential equation from y is equal to x plus a over x. And as I've said before, every single time you actually have one arbitrary constant, you actually differentiate once. Now, even without being told, you can already see in this question, the arbitrary constant is that capital A. So let's solve this. So we have y is equal to x plus a over x. Now we're going to label this as equation 1. Now we're going to differentiate that with respect to x. But before we do that, we can actually see that a over x can actually be represented as a times x to the power negative 1. Now differentiating this, we'll have it as 1 minus ax to the power negative 2. As you can see, when you differentiate x, we get 1. And then this negative here shall come and affect this plus sign, and we'll have it as minus ax to the power negative 2. And that's what you get when you actually differentiate that. Remember, a is a constant, so it remains unaffected in that case. Now we can already see that we'll have it as dy dx is equal to 1 minus a over x squared. Now that we have this, we've actually said before that in this case we only differentiate once. So we're not going to differentiate for the second time, but we still have that a value there in our equation. But let's first label this as equation 2. So how do we eliminate that a? What we're going to do is we're going to go back to equation 1 and we're going to make a the subject and substitute the value of a into equation 2. So from equation 1, we're going to make a the subject, and then we'll have it this way. So this is equation 1. As you can see in equation 1, I've already dealt with it and made x the LCM. So the LCM is x, and as you can see, this x will multiply this x squared, because x divided by 1 is x, and then x times x is x squared plus that a. So that's what happens when you get the LCM right there. Then you can actually say when you cross multiply, we'll have it as xy being equal to x squared plus a, of which a, when made the subject, shall be equal to xy minus x squared. So now that we know the value of a, we're going to substitute that in equation 2. So equation 2 shall now become dy dx is equal to 1 minus bracket xy minus x squared over x squared. Now as you can see, I chose to put my value of a inside brackets. And why is that? It is because there is a minus sign right here. So to actually protect it, I actually chose to put that in bracket. Now that is the safest way to do it. Now when you find the LCM in this case is x squared, and then as you can already see, because we actually have this 1 is over 1, x squared divided by 1 is what? X squared. So x squared times 1 is x squared. So I have x squared minus that right there. So now we can safely open the brackets, and then we'll have it as x squared minus xy plus x squared over x squared. Now as you can see, the x squared values add together at the numerator, and we'll have it as 2x squared minus xy over x squared. Then you can actually see that I can actually factorize out the x in the numerator, and then I'll remain with that. Now you can see that it will actually reduce with the value at the denominator, and then I'll be left with 2x dy dx being equal to x minus y over x. Alright, so next I can cross multiply, and I'll have it as x dy dx being equal to 2x minus y. So bring everything to the left hand side, I'll have it as x dy dx minus 2x plus y is equal to 0. So therefore the required differential equation is x dy dx minus 2x plus y is equal to 0. So question number 3 is going to be a question from UNEB 2011, and this was question number 8. So being told to form a differential equation by eliminating the constants a and b from x is equal to a cos t plus b sin t, and hence state the order of the differential equation formed. Now, as you can already see, we actually have two constants involved, two arbitrary constants. So what happens is, in this case, we already know that we're actually going to need to differentiate 2 times. So this is what we have, and we're going to make that equation 1. So we're going to differentiate with respect to t. So where both a and b are arbitrary constants, we're going to differentiate the equation twice. So we'll have dx dt. So since we're differentiating with respect to t, we'll have dx dt being equal to, we know that when you differentiate a cos t, we actually get a negative sin t. So that's why we have it as negative a sin t. Then when we differentiate a sin t, we get a positive cos t. So that's why we have it as b cos t right there. And now we know we actually have to differentiate for the second time. So the second derivative shall be, so when you differentiate this sin t again, we get a positive cos t. But because there was already a negative here, we'll actually leave it as negative a cos t. Then on this other side, when we differentiate the cos t, we get a negative sin t. And that's why we have this plus here changing to a minus. Alright, so now that we've done that, we can already see that we still have the a and b values involved. So that means somewhere along there, we're going to actually have to substitute for them. Now when I look here in the second derivative, I see something unique. I can see that I can actually pull this minus sign out of the brackets. So that means my second derivative can be a minus bracket a cos t plus b sin t. So when I do that, I actually see something very unique. I can actually see that x is actually equal to a cos t plus b sin t. So that actually means I can substitute the value of x to where I actually have this value right there. So that means if x is equal to a cos t plus b sin t, our second derivative shall be equal to negative x. And then I can actually rearrange that, and it will become d squared x over dt squared plus x is equal to 0. And that shall be the differential equation that we were asked to form. Now we can already clearly see that here the highest derivative is the second derivative. So that means that this is second order. So question number 4, being told to form a differential equation from the equation y is equal to ax squared plus bx. So you can already clearly see that we're dealing with two arbitrary constant right here, and that is a and b. So that means we are definitely going to have to differentiate twice. So now we have y is equal to ax squared plus bx, and that shall be our equation 1. So where both a and b are arbitrary constants. So when you differentiate for the first time, we're going to have dy dx is equal to 2ax plus b. Then we differentiate for the second time, we shall have it being equal to 2a, because the b shall now fade away. But now up to this point, we've actually not yet gotten we've not yet fully eliminated the values of a and b. So we actually have to form a technique to actually eliminate both of them. So this is what I've chosen to do. As I can see, is in the third equation, I only have the value of a, and then in the first equation, I have it this way. So what I'm going to do is, I'm going to make b the subject inside this equation right here. That's what I'm going to be doing. And then right here, I'm also going to make a the subject. And then the final values that I get from both sides, I'm going to substitute into equation 2 to get the final differential equation. So we're going to make b the subject in equation 1, and then we know that equation 1 is written this way. So we'll have y minus ax squared is equal to bx, and then b shall actually be equal to y minus ax squared over x. So that is the value of b. So now I'm going to go to equation 3, and then I'm going to make a the subject. So you can actually see that this is what we have. So a shall actually be equal to a half times d squared y over dx squared. Alright, so next we're going to substitute for b in equation 2. So we'll have it as dy dx is equal to 2ax plus 1 minus ax squared over x. So next step shall be to find the LCM. The LCM shall actually be x. Then x divided by 1 is x. X times 2ax shall actually be equal to 2ax squared. And then we'll have it this way. Now I could cross multiply and I'll have x dy dx being equal to 2ax squared plus y minus ax squared. Now the next step is I can actually take the y to the other side and I'll have it as x dy dx minus y is equal to 2ax squared minus ax squared. Now I can see that these two values are actually similar, so they can actually subtract each other and I'll have it as ax squared. So now next I actually have to substitute in the value of a, because now that b is gone, I actually now have to substitute the value of a. But before I do that, let's first make a the subject. So now I have a being equal to x dy dx minus y over x squared. Now I can already see that this can be represented this way. It can be represented as 1 over x squared times x dy dx minus y. Then I can actually multiply this inside and I'll have 1 over x, because 1 over x squared times x, a value cancels and I'll have 1 over x remaining right here. Then this times y will be y over x squared. But a is a half d squared y over dx squared. So when I plug that in, I'll have it this way. So now I have a half d squared y over dx squared is equal to that. Now I can see that I can actually cross multiply, and this a half, these two can multiply these values right here and I'll have it that way. So when I open brackets, this is what I have. I have 2 over x dy dx minus 2y over x squared. So bringing everything to the left hand side, I'll have it as second derivative of that minus 2 over x dy dx plus 2y over x squared being equal to 0, and that is the differential equation. And the reason I know this is now okay is because a and b have been successfully eliminated. Alright, so next we move to a question from UNEB 2016, and this was question 13a. So being told that if x squared plus 3y squared is equal to k, where k is constant, find dy dx at the point 1, 2. Now this basically, these are coordinates. It means the value of x is 1 and the value of y is 2. But before we do that, we actually have to first eliminate this constant k. So this is what we have. So when you differentiate this, every individual, differentiate x squared and you have 2x, differentiate this and you have 6y dy dx being equal to, differentiate this constant and you'll be left with 0. So we've already eliminated the constant, so it's actually an easy one. So the next step shall be to actually plug in these coordinates right there. So where there is x, we're going to put 1, and where there is y, we're going to put 2. So this is what we have right now. 2 times 1 is 2 and 6 times 2 is 12. So this is what we have. So now basically I can actually take the 2 to the other side and I can actually use that to reduce the value. So dy dx should actually now be equal to the negative 2 over 12, which is actually equal to negative 1 over 6. So basically this is the differential equation that they wanted. So this is another question from UNEB 1998, and this was question 13a. So being told that given that y is equal to e power 2x sine 3x, prove that the second derivative, I mean d squared y over dx squared minus 4 dy dx plus 13y is equal to 0. Now a proof question is definitely the same as a formation of a differential equation question. So it's basically the same thing. So we're going to actually follow the same steps. Now the difference in this case is when we look at our final proof, we can actually see that the y value is actually preserved. So that actually means that we actually have to look forward to actually preserving the y value as much as we can. Now I'll show you what that looks like. So this is what we have. We have y is equal to e power 2x sine times sine 3x, and shall be our equation 1. So we can actually see that when we differentiate this, actually we're going to differentiate this. When we do that, we're actually going to use product rule in this case. Now another thing that is also important for you to identify is, because you see second, you can actually see that the highest derivative is the second derivative right here. It basically means that we will have to differentiate twice. Alright, now differentiating equation 1 with respect to x for the first time, we can let u be equal to e2x. Remember, we're using product rule. And then du dx should actually be equal to 2e2x. And we're going to let v be equal to sine 3x, and then therefore dv dx should actually be equal to 3 cos 3x, because that's what we get when we differentiate that. Then from product rule, we know dy dx should actually be equal to u dv dx plus v du dx. So therefore, plug in the values, and this is what we end up having. Now when we multiply those, we are left with dy dx being equal to 3e2x cos 3x plus 2e2x sin 3x. But then I want you to observe something. Now as you can see, the goal is also to preserve the value of y. As you can see, these values right here are actually equal to the value of y, because y is equal to e2x sin 3x. So that means we're going to substitute that with y. So we'll now have dy dx being equal to 3e to the power 2x cos 3x plus 2y. Now the next step after this is going to be equation 2. Now the next step shall be to get that second derivative. So differentiating equation 2 with respect to x. So we'll have the second derivative being equal to that. Now as you can already see, this side here shall actually still also require product rule, and then this can actually be differentiated directly. So after differentiating this from product rule, I'll have 3 into e2x times negative 3 sin 3x plus cos 3x times 6e2x. Then plus, when I differentiate 2y, I'll have 2y dy dx. Now when I simplify this, I'll have multiply this in, and I'll have negative 9e2x sin 3x plus 6e2x cos 3x plus 2 dy over dx. But we remember that y is equal to e2x sin 3x, because you can already see right here that there is actually the value of y in existence. So we're going to also plug it in there. So our second derivative shall actually be equal to negative y plus 6e2x cos 3x plus 2 dy dx. Alright, so now the next goal shall be to eliminate these values of e2x and cos 3x, because I don't see them in our final proof. So what are we going to do? So we're going to have to find a way of substituting for them. Now the first thing I can see here is actually I can factorize out a 2. Then I'll have it as 2 into 3e2x cos. I'll have it as 2 into 3e2x cos 3x plus dy dx. Now this shall be our equation, and this shall be our equation 3. Now from equation 2, I can actually get a value for this and actually substitute for that. Now remember that dy dx was equal to 3e2x cos 3x plus 2y. So basically I'm going to make this value here the subject. So I'll see that 3e2x cos 3x should actually be equal to dy dx minus 2y. So substitute that into equation 3, and this is what we end up having. So now where there is this 3e2x cos 3x, we're going to place this value right here. So that's what we end up having. Now I can already say that this and this are similar, so I'll have them combined together, and then I'll have 2 dy dx right there minus that 2y. So next step shall be to multiply these 2 inside the brackets, and then I'll have this. So I'll have negative 9y plus 4 dy dx minus 4y. So rearrange the terms, and this is what I end up having. Now you can actually see that 9y plus 4y shall actually be equal to 13y. So this is what I have. And then basically when I rearrange these, they will actually now be similar to the proof that we are looking for, and this is the answer that they wanted. Alright, so question number 7, we're being told that if y is equal to tan into bracket 1 plus x over 2, show that the second derivative, d squared y over dx squared minus y dy dx should actually be equal to 0. Now there's something you also note in this question. You can actually say that we actually have the value of y in our final proof. So that means we actually have to look to preserve it. And then we also have a second derivative. So that actually means we're also going to be differentiating 2 times. Alright, so let's look at the solution to this. So we have y is equal to tan bracket 1 plus x over 2, and this shall be our equation 1. Now to preserve this, I would encourage you to never take this, in this case, don't take the tan to the left hand side to make it tan inverse of y, because that will actually not work in this question. Now, what we're going to do is we're going to just differentiate this with respect to x and keep everything on the same side. Now we can already see that this right hand side here, to differentiate it, we should actually have to use chain rule. So we're going to let t be equal to 1 plus x over 2. That means t shall actually be equal to, can be written as 1 over 2 plus x over 2. And the t dx shall actually be equal to a half. Then y shall actually now be equal to tan t. So dy dt now can be seen as sec squared t, as you can see right there. But remember that from chain rule, dy dx shall actually be equal to dy dt times dt dx. So now this is what we end up having, sec squared t times a half. So dy dx shall actually be equal to a half sec squared t. But remember t is equal to 1 plus x over 2. So we're going to plug that in and we'll have it this way. So therefore our dy dx shall actually be equal to a half sec squared, then bracket 1 plus x over 2. Now this is now the first derivative. Now the reason this is useful is you can actually see that inside a sec here, we can actually see that there is actually a tan involved. So now that can be written as 1 plus tan squared into bracket 1 plus x over 2. Now because the goal is to preserve the value of y until the final proof, that means we're actually going to substitute y where there is tan 1 plus x over 2. Now this is what I have. So now remember that y is tan into bracket 1 plus x over 2. So I'm going to plug it inside there, and then I'll have dy dx being equal to a half into bracket 1 plus y squared. That shall now be our equation 2. Alright, so now the next step is we're going to differentiate for the second time. Now but before we do that, we can actually see that our dy dx can actually be written this way as a half plus y squared over 2. So when I differentiate this, as you can see, where there is this y, definitely this a half becomes a 0. So there is this y, we can actually say this 2 comes down, and we can actually say it cancels this 2, and we'll be left with y dy dx. Now this is an example of something, an implicit function. So that's why whenever we differentiate a y, we actually multiply to it a dy dx. Alright, now rearranging this and bringing all values to the left hand side, I'll have d squared y over dx squared minus y dy dx being equal, shall be equal to 0, and this is the answer they wanted. Alright, so moving on to the next question, we're being told if y is equal to tan inverse of x, show that 1 plus x squared d squared y over dx squared plus 2x dy dx shall actually be equal to 0. Now this is a different kind of example. As you can see, unlike the former examples, in this case we don't need to preserve the y value. So that actually means that we should actually just differentiate as it goes. But you can also notice that we actually need to also find the second derivative. Now we have y is equal to tan inverse of x, so we're just going to differentiate it as it is. So differentiating that 1 with respect to x, we'll have dy dx should actually be equal to 1 over 1 plus x squared. And then to find the second derivative, we're actually going to use quotient rule, as you can see, because this is actually quotients, 1 over 1 plus x squared. So we're going to let u be equal to 1, and then we can actually see that du dx should actually be equal to 0, and then v should actually be equal to 1 plus x squared, of which dv dx should actually be equal to 2x. So from quotient rule, the second derivative shall be found using this formula. So we're going to plug in the values, and then when you plug in the values, we'll be left with minus 2x over 1 plus x squared, and then out of that bracket we're going to square that also. Then this can actually be separated this way. Now this can actually be written as this. Now remember, the denominators are actually squared, so that actually means it can be written as minus 2x over 1 plus x squared times 1 over 1 plus x squared. Now you may wonder why split this into two different parts. The basic reason is I want to find a way of substituting this back here, because you can see that in our final proof the dy dx is still involved, and yet we've already differentiated twice. So that actually means that now wherever there is 1 over 1 plus x squared, we're going to plug in dy dx. That is the purpose for that. So now basically what we now have is that, so remember dy dx is 1 over 1 plus x squared, so I'm going to substitute that in and I'll have it this way. So the second derivative shall be equal to negative 2x over 1 plus x squared times dy dx. So now the next step shall actually be to rearrange everything. Now because there is a minus sign in front of all these, I'm actually going to take them in and to the left hand side, and I actually have a plus sign. Now the next step is I can actually see that this is 2x over 1 plus x squared. So that actually means that I can actually make this the LCM on both sides. So that actually means that here the coefficient is 1. So the LCM shall actually be equal to 1 plus x squared, and then 1 plus x squared divided by 1 shall actually be equal to 1 plus x squared. Multiply the numerator and I'll have it this way. Now the next step shall actually be to cross multiply. So when I cross multiply, this shall actually, this times 0 is 0. So on the left hand side I'll be left with bracket 1 plus x squared, second derivative plus 2x dy dx being equal to 0, and that is the proof that they wanted. Alright, so question number 9, we're being told that given that y is equal to e to the power tan inverse of x, show that bracket 1 plus x squared d squared y over dx squared plus bracket 2x minus 1 dy dx shall actually be equal to 0. So this is another proof question. Again, note that there is actually second derivative involved, and then we actually don't need to preserve the value of y. So this is actually going to be an easy one. So as we've been given in the question, y is equal to e tan inverse of x. Now, in this case, we're going to have to first eliminate that e to differentiate more easily. So we're going to introduce ln to both sides. So if we introduce ln to both sides, we'll have ln y is equal to ln e tan inverse of x. But remember that wherever we introduce a ln and there is an e, the e is eliminated. So we'll actually be left with ln y is equal to tan inverse of x. Now, we're going to differentiate both sides. Now remember that the derivative of ln y shall actually be equal to 1 over y, but because this is now implicit and we're differentiating a y on the left hand side, we're going to multiply to it dy dx, which is equal to, then remember that the derivative of tan inverse of x is 1 over 1 plus x squared. So in the cross multiply, we'll have dy dx is equal to y over 1 plus x squared, and that shall actually be our equation 2. So now next we actually have to find the second derivative. So now as you can see, in this case we also have to use quotient rule. So u is y, we're going to let u be y, and then to find du dx we shall actually see that du dx shall actually be equal to dy dx. And then we're going to let v be equal to 1 plus x squared, and then dv dx shall actually be equal to 2x. Now the reason why du dx is actually equal to dy dx is because we're going to do everything has to be done in this case with respect to y. So that's why we'll have this as dy dx. Now from quotient rule, we're going to have the second derivative as being equal to, so this is the formula we're going to use. So plug in the values and I'll have this. So when I simplify, I'll have this value as written as this. Alright, so now this is basically what I have. Now that I found the second derivative, I actually have a dy dx value right here. So that means that's okay. Now what I actually see in my final proof is I see y values are actually all eliminated. So that actually means I actually have to find a way of eliminating this y value. So good enough is from equation 2, I can see that dy dx is equal to y over 1 plus x squared. So that actually means I can make y the subject and y shall be equal to bracket 1 plus x squared times dy dx. So when I plug that back in, I'll have it this way. So wherever there is a y, we're going to put in this value right there. So as I can already see here is I can actually factorize out some values. So I can factorize out 1 plus x squared and dy dx, and inside the brackets I'll be left with 1 minus 2x. And then this is what I have. So now I can already see that this value and this value are similar, so they'll actually reduce. So this and this reduce, and then this will be left to a power 1. So this reduces power, and then I'll be left with 1 plus, then I'll be left with 1 plus x squared, as I can see right there. So I can cross multiply. So when I cross multiply, this is what I have. So I can actually now bring every value to the left hand side, and this is what I end up having. Now to make sure everything is like in the final proof, I can actually say in the final proof that this is written as a plus sign. So what I can do is I can actually plug this negative in to these brackets and then leave that as a plus, and then this plugged in, I'll have plus 2x minus 1, and this is the proof that they wanted. Now there is an exercise for you. I encourage you to try out these questions, and I believe that after this you'll actually have a better understanding. So many of these are proof questions, so basically you can just compare your answer with the proof that I actually give you right there, except in 6 and 7 I've actually given you the answers in this brown color right there. Thank you so much for watching.
Thank you so much for watching this video. I hope the video really helped you. I hope the numbers were sufficient for you. If this video was of help to you, feel free to give the video a like, a thumbs up, and then feel free to share the video with all those that you can and help them out if the video really helped you. And then you can leave a comment down in the comment section for me, and I'll get time to reply to you. Thank you so much for watching. I'll see you in the next video.